This video is going to talk a little bit about dot products and kind of how we can use them, but also to realize that we don't always necessarily need the dot product to find questions that would relate to something like that. Many books talk about the projections of one vector onto another, sort of talking about, okay, how do you represent vector u, right? Is a projection onto vector v or v onto u? And they kind of do this fancy formula down here at the bottom. But what I want you to realize, first of all, is that really vectors, again, are just forces, directed forces, essentially, direction and magnitude. So if we had a boat weighing 1 ton sitting on a hill, right? Again, gravity is that red line that we've got going on here. Gravity would be pushing directly downwards, right? That's that red line dropping straight down, the diagonal of our parallelogram there. So our boat's sitting on a hill at a 30-degree angle of elevation. So the other thing we can realize is, again, that 30 degrees, right, is traveling right here, right? That's our 30 degrees. Well, the nice part about that being 30 degrees is with that gravity going straight down, if we sort of separated that vector into its components, one of our vectors is going to travel straight down the hill, right? That's that black vector going on right here. It's traveling straight down the hill. And the other vector is that orange vector. That's basically the weight being supported by the hill, right? The hill is doing some of the work, right? The boat's not going through the hill. But if the hill supports some of the work, right, all we have to do is kind of equalize that black vector to keep that boat from rolling down the hill, right? We want to kind of use that length there. So essentially, the nice part is, again, if we work a little geometry, if that's a 30-degree angle on the hill, that makes this angle, right here, 60 degrees, right, to make that perfect perpendicular with the hill. And if that's 60 degrees, again, this would be our 30 degrees inside of here again, right, because that's perfectly horizontal to vertical. And basically we figure out that this bottom angle down here, right, is going to be a 60-degree angle, right, on there. So again, the black vector is going to be the force of the roll that we need to oppose, right, to keep that boat from rolling down the hill. But we've got all these angles worked out. We also know that, again, the boat is weighing 2,000 US pounds. So again, that red vector, right, is going to have a magnitude, right, of 2,000. Right? Let's see if I can write that on here. That's going to be 2,000 on there. And it means that, again, all we need to do is find the length of, right, this vector going on there. Well, we've got the hypotenuse for a 90-degree right triangle. We've got that 60-degree angle to work with, or the 30, either one works. And again, we're trying to find, let's go ahead and go from the 30 up here, the opposite, right? So we can say that the sine of 30 degrees, and again, I like that because remember, that's just a half, but the sine of 30 degrees is equal to the opposite. So our black line there, we'll just call it x, divided by 2,000. Well, x over 2,000, I can just multiply the 2,000 over to the other side, and basically, how hard do we have to push to keep that boat on the hill? Well, basically 1,000 pounds worth of force. There you go. Again, we didn't necessarily have to do that full projection idea down at the bottom. Feel free to read your book and talk all about projections, though. They're not bad things. One other application, a really good application of a dot product, though, a good place we can use a dot product, is finding the work done between two objects. The work done is basically the dot product of the force vector, how much force it takes to move something, times its distance vector, or sort of direction vector. So you use 100 pounds of force to lift a barbell straight up. So if we took a look at that, basically we're going to lift directly upwards. So the vector 0, 100 makes sense, right? We're going straight up with our vector, right? Calculate the work done in moving that barbell 2.5 feet. So again, we're going straight upwards with our direction, right? So 0, 2.5 makes sense. And if we take their dot products, right, 0 times 0 is 0, 100 times 2.5 would be 250. And essentially we're moving feet and we're moving pounds, so we call this 250 foot-pounds of work. You push a lawnmower at an angle of 40 degrees with the ground, so now this time we're not going directly upwards, but we can still set up a vector for this. You're going to push with a force of 30 newtons. So if I set up a couple of vectors, 30 newtons at 40 degrees, right, nice trig vector there. How much work is done to push the lawnmower 50 meters? Well, now the 50 meters is going to be directly along the ground, right? So we can just say that's 50 to the right. 50 comma 0 makes sense there. We'll quickly take a dot product. So again, 50 times 30 cosine 40 plus 0, right, times the rest of that stuff. So we don't really need to say 30 sine 40. Pop that in the calculator though. And this time again, we were pushing with newtons as our force, but we traveled meters. So again, 1,148.067 Newton meters. Newton meters. So the idea is if you can set up a couple of vectors and take their dot product, again, you can find the work it takes to complete those questions. Let's take a look at a couple more very quickly. Let's say you had a tractor and it's trying to pull a log, right? Maybe a really heavy log with a squirrel on it, right? Well, you can pull that tractor along 800 meters, right? We're going to pull that log along the ground, those 800 meters. But realize that technically with where we have the chain, our chain is not pulling directly to the right. Our chain is at an angle to the ground, right? Our chain's got a little angle there. So what we want to figure out is, again, your tractor is going to pull a log, a wooden one, not a mathematical log, 800 meters, and the tension in the cable connecting the tractor and log is about 1,600 kilograms. So our magnitude, right, of our chain is 1,600 kilograms with a 30-degree angle, right, of elevation to the ground, okay? But we're going to pull the log 800 meters directly along the ground. Well, let's set up a couple of vectors. Our direction vector, right, would be 800 meters to the right, comma, 0 meters up and down. And our chain here, right, would be at 1,600 kilograms, cosine of the angle, sine of the angle. And the nice part is when we take that dot product, again, that 0 is going to end up getting multiplied by our 1,600 times the sine. So really we just end up with 800 times 1,600 cosine of 30, right? And essentially plus 0, right? Plus 0, if we wanted to write it out, times 1,600 sine 30. It doesn't really matter a whole lot because that turns to 0. And we just have to type it in the calculator then. 800 times 1,600 cosine 30. Make sure you're in degree mode. And we get 1108512.517. And again, let's throw a couple of commas in there. So a little over 1 million, and we're talking in kilogram meters, right? So we're just going to say kg meters. I know it's kind of a weird label, but again, that's the way work works. Let's do one more very quickly. Let's say you're trying to open up a barn here, right? Bessie wants to go out, right, to get some hay, maybe some grass. So we're going to pull this door along a railing, but again, we're not as tall as the railing usually. So again, we're going to pull this rope from the ground here, right? And so what's going to happen is we're going to move the door 8 feet. Well, the 8 feet is directly sideways, right? That 8 feet's going, right, 8 feet to the right, not going up and down at all, right? Hopefully our railing is nice and level. Dot, well, the rope, though, is being pulled at 70 pounds and at an angle of 58 degrees, right? 58 degrees with the horizontal there. So cosine 58 degrees, sine 58 degrees. Now you might be saying, well, wait a minute, isn't that 58 degrees sort of at a negative angle? Well, yeah, technically, but remember cosine of negative 58, which is the only part that's going to matter, because again, we're going to end up saying plus 0 again here. But the cosine at 58 degrees is the same thing as the cosine at negative 58 degrees, right? That odd even function, so we can get rid of that negative. So basically, we just need 8 times 70 cosine, right, 58. And very simply, 8 times 70 times the cosine at 58 degrees is 296.755, right? And again, we're pulling at pounds and we're pulling feet, so we call that foot pounds. Okay? So 296.755 foot pounds. I hope that helps you, again, finding the amount of work it takes to accomplish a task. If you have any questions, talk to your teacher. And otherwise, have a great day.